So far we have seen how to draw Bode plot for 1 by S, first order factor in the denominator, first order factor in the numerator, repeated poles and repeated zeros. In addition to that, we have seen first order system and first order factor in the denominator and numerator, that and all we have seen. Today, let us see how to draw Bode plot for second order system. Second order factor in the denominator as well as numerator. If you consider any transfer function, definitely there will be gain. It may have poles at origin. It may have poles at zeros at origin. Both may not exist, but anyhow, both may not exist simultaneously. One will get cancelled the other. Definitely n minus m poles will be there if m is less than n. And the first order factor in the numerator and the first order factor in the denominator and the repeated factors, that also we have seen. Now let us see second order factor in the denominator, that is tau 3 s square tau square s square plus 2 zeta omega, 2 zeta tau s, 2 zeta tau s plus 1. This is second order factor in the denominator, or T4 s square plus 2 zeta tau s plus 1. Why this happens while factorizing means, if the poles are real, you will get the first order factor. The poles are complex, we won't convert into factor. In that case, we will keep it as second order factor. That's why if you factorize a given transfer function, the possibilities are, these are the possibilities. For that, already we have seen 1 by s in the numerator, k, first order factor, repeated factors, that and all we have seen. Only pending is this. So g of s equal to 1 upon tau s square s square plus 2 zeta tau s plus 1. If this factor is there, what is the Bode plot that we are going to see today? If you convert this into sinusoidal transfer function, replace s by j omega, then what you will get? Minus omega square t square for this, plus 2 zeta j 2 zeta tau omega plus 1. This you will get. What is modulus of g of j omega? Modulus of g of j omega equal to 1 upon square root of real part square, that is 1 minus omega square t square is the real part, whole square, plus imaginary part is 2 zeta tau, imaginary part is 2 zeta tau omega. So that square, 4 zeta square tau square omega square, that is imaginary part. This is modulus of j of j omega. If you write this in decibel, 20 log 1 by, this is equal to 20 log 1 by square root of 1 minus omega square t square whole square plus 4 zeta square t square omega square. In dB, decibel scale, In that case, again, we will consider two cases. One is omega tau is far, far greater than 1. Omega tau is far, far greater than 1 means the zeta is always less than 1. Here, what you will get is omega power 4 20 log. This 1 becomes negligible because as omega tau is far, far greater than 1. That's why 1 becomes negligible. This becomes omega power 4 square root of omega power 4 t power 4 plus 4 zeta square t square omega square. This is also negligible. We'll compare with omega power 4 t power 4. 4 zeta square t square omega square also negligible because fourth power is second power multiplied by zeta, that is less than 1. That's why this is also negligible. That's why this becomes that is approximately equal to 1 by 20 log 1 upon square root of omega power 4 t power 4 omega square t square. This is approximately equal to this. That is equal to 20 log omega square t square. If it bring to the numerator, you will get minus sign to the power minus 1. Therefore, minus 20 log omega square t square. If you bring this t square, if you write instead of omega square t square, if you write omega, this is also equal to minus 20 log omega tau whole square. Omega tau whole square. Therefore, this becomes minus 40 minus 40 log omega tau. Now we will substitute omega equal to 1. Omega equal to 1 by t. If you substitute, what you will get? When omega equal to 1 by tau, if you substitute 1 by tau, this becomes 1. Therefore, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. When omega equal to 10 by tau, if you substitute 10 by tau, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 1, that is equal to minus 40 dB. When omega equal to 100 by tau, another 10 times increase, you will get 20 log modulus of g of j omega equal to minus 40 log 100 means 10 square, that is equal to minus 80 dB. Log 10 equal to 1, that square becomes multiplication, that's why minus 80 dB. So the slope is, it increases at the rate of 40 dB per decade. Another case is when omega tau is far, far less than 1. This 1 is considered, this omega square t square, this both are negligible. That's why 1 you will get. Root 1 is 1. Therefore, 20 log g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. Therefore, what is the plot for the second order? The plot is 0.1, omega equal to 0.1, 1, 10, 100 log omega, logarithmic scale. Here, let us assume that this is 1 by t, because we do not know the value of t. 100 by t, 0.1 by t. Up to 1 by t, it is 0. Up to 1 by t, it is 0. up to 1 by t, it is 0 dB. After that, it decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. If you find the error, what is this is the plot up to corner frequency 0. After that, it decreases minus 40 dB per decade. If you consider complete 20 log g of j modulus of g of j omega equal to 20 log minus 20 log square root of 1 minus omega square t square whole square plus 2 zeta 4 zeta square t square omega square. If you consider complete of this, it is function of zeta. It is function of zeta. Zeta value decreases, it is in the denominator. It is in the denominator. That's why as zeta value decreases, the magnitude will increase. The magnitude will increase. That's why the plot for zeta equal to 0.7 will be like this. The zeta for 0.7 will be like this. This is for zeta equal to 0.7. If you increase further, there will be a sluggish, maybe zeta greater than 0.7. If it decrease, what will happen? Suppose zeta is 0.2 means it will come like this. Zeta equal to 0.2. This is zeta equal to 0.5. Like that. So there will be a large error at corner frequency for second order system. That is the only drawback. Anyhow, for 0.7, it gives approximately this value. If zeta equal to 0.7, it gives almost minimum error. Suppose if you have a second order factor in the numerator, that is what g of j omega equal to g of j omega equal to g of j omega equal to tau square s square plus 2 zeta tau s plus 1. If you give like this, then what is the plot is just opposite to this. Here, it decreases at the rate of minus 40 dB per decade. Instead, it will increase. Therefore, the plot will be like this. Up to 1 by tau, it is 0 dB. After that, it increases at the rate of 40 dB per decade. This is second order factor in the numerator. Here also depends upon the zeta value. It will be like this. This is for 0.7. Zeta equal to 0.7. If zeta decreases, you will get like this. If zeta increases, you will get lag value. So error will be minimum when zeta is around 0.7. So approximate plot is this: up to 1 by tau 0. After that, it increases at the rate of minus 40 dB per decade. That's all. We have seen all factors. Hereafter, we can draw Bode plot for any function. Before going that sum, the procedure to draw Bode plot, let us consider this g of s equal to k and tau s plus 1 and tau square s square plus 2 zeta tau s plus 1 upon s then tau 1, tau 2, tau 3 s plus 1. This is tau 4 s square plus 2 zeta tau 4 s plus 1. 4 time constants are there. Let us assume that T1 is T4 is greater than T2 greater than T3 greater than T1. Which is the smallest value? T1. T1 is the smallest value. Therefore, largest corner frequency is 1 by T1. Omega 4 equal to 1 by T4. Omega 2 equal to 1 by T2. Omega 3 equal to 1 by T3. Omega 1 equal to 1 by T1. If you write in terms of omega, omega 4 is the smallest. Omega 2 next. Then omega 3 next. Omega 1. Which is the largest? Omega 1 is the largest. So, what is the plot? Let us mark all the corner frequencies first. Omega 1 is largest. Therefore, first will be omega 4. Next will be omega 2. Omega 3. Then omega 1. Am I correct or not? Whether I correctly marked? Correctly marked. Except K, all other. One more is S is there. Except K and X, I marked all. For all factors. Omega 4 is what? For T4. Omega 4 is for T4. What is the corner frequency for this? What is the corner frequency for this? For this corner frequency is omega 4. Therefore, for this up to omega 4 it is 0. Am I correct or not? Up to omega 4 it is 0. After that it decreases. It will decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. It decreases at the rate of minus 40 dB. Minus 40 dB per decade. Because it is second order factor. That's why it decreases. But we can extend up to omega 2 only. Omega 2 is where? In the numerator. What is its slope? Plus 40 dB. That's why omega 2 to omega 3 again it will be horizontal line. Again it will be horizontal line. Omega 3 is again in the denominator but first order factor. That's why it will decrease at the rate of 20 dB per decade. Minus 20 dB per decade. It will go up to omega 1 only. At omega 1, again numerator factor. That's why 20 getting cancelled. Again it becomes horizontal. Again it becomes horizontal because for this 20 dB plus 20 dB per decade, for this minus 20 dB, for this minus 40, for this minus 40. So all equal, plus 40. This is plus 40. That's why all equal, that's why getting cancelled. Finally, it becomes horizontal. Suppose more denominator factor means finally it will decrease, further decrease. We plotted, if you know the corner frequencies, we can draw the Bode plot without doing any calculation. Now, how to incorporate K and the S? How to incorporate K and the S? What is K? For K is 20 log K in dB scale. In dB scale, 20 log K. 20 log K, K equal to 10 means it is 20 dB. 20 dB. This is the plot for K. This is what? 0 dB. Therefore, 20 dB will be here. 20 dB will be here. 20 dB. This is plot for K. This is plot for K. 20 dB. K equal to 10. That's why 20 dB. 1 by omega, 1 by S. For that, what is the plot? It is inclined at minus 20 dB per decade for the entire plot. Minus infinity to plus infinity, it decreases at the rate of, we have already seen. It decreases at omega equal to 1. At omega equal to 1, it crosses 0 dB. That is the only point that we know when omega equal to 1, 1 by s means what? 1 by 1, 20 log 1 equal to 0, therefore 0. It decreases at the rate of 20 minus 20 dB per decade. This is for 1 by s. I am writing a plot for 1 by s also. Let us assume that omega equal to 1 is here. Omega 4 is less than 1. Let us assume. Therefore, this is the plot for 1 by s. 1 by s. We have to add these three together. If we add these three together, we will get the complete plot. So I am telling you how to, if you know the transfer function, you can draw the frequency response. So for K, you have to lift everything by 20 dB. You have to lift everything by 20 dB. Therefore, 0 dB becomes 20 dB. Am I correct or not? If you lift the entire plot by 20 dB up, you will get 0 dB becomes 20 dB. That's all. So we included K. The only thing is we have to include that 1 by S. If you include 1 by S, what will happen? This horizontal line is, the slope is 0 dB per decade. But because of this, it becomes 20 dB per decade. Therefore, this becomes, this 0 dB becomes minus 20 dB per decade. This 40 dB becomes minus 60 dB per decade. This horizontal line again becomes minus 20 dB per decade. This minus 40 becomes, this 20 becomes minus 40. This horizontal line again becomes minus 20 dB per decade. The slope is now changed because of this 1 by S. The slope is changed. The slope is changed. So what we have to do is, now we have to shift this up by, so here we have to draw L. Here already this is shifted for 20 dB. Here instead of horizontal line, we have to draw yeah, 20 dB line. 20 dB line. Again, this becomes 60 up to omega 2. Again, this is 20 dB line. Again, this becomes 40 dB. This becomes 40 dB. Again, 20 dB. Like that, the slope will be changed, 1 by S. The slope will be changed. So instead of horizontal line, its slope is minus 20 dB per year. Instead of 40 dB, it becomes 60 dB. So for the entire plot, we have to add 20 dB. So we can draw the rough plot. We can draw the rough plot. So how to draw that, we'll see here. 1 by K by S, we have to take. That K by S is, if you draw only for K by S, for K it is 20 dB, 1 by S at omega 1 equal to, you will get a 20 dB slope at, this is for 1 by S, its slope is minus 20 dB per decade. This is 0.1. That's why for K you will get a line here. For K equal to 10. That is 20 dB. If you combine these two, what will happen? If you add 20 dB at every point means this will shift up to by this, like this. This is 10 by S. Am I correct or not? This is 10 by S. Now we have to add the previous. This is omega 4. Omega 4. This is omega 2. Am I correct? Omega 2. This is omega 3 and this is omega 1. Now we have to add that previous plot. This has to be added. This is 40 dB up to omega 2 and then horizontal, then 20 dB, then horizontal. Now we have to add this and this. One more time we are seeing, that's all. So here, this is horizontal, this is inclined line. That's why this we have to take, that's all. This we have to take up to omega 4. After omega 4, what is the total slope? This is 20 dB, this is 40 dB, minus 40 dB per decade, because second order factor. This is 20 dB. Now we have to draw up to omega to 60 dB per decade. So up to omega minus 60 dB per decade. After this, what will happen? This is 0, but this is 20 dB. That's why from omega 2, we have to draw only 20 dB, minus 20 dB per decade, up to omega 3. At omega 3, this is 20, this is also 20. Therefore, we have to draw at 40 dB. We have to draw at minus 40 dB per decade line up to omega 1. After omega 1, only 20 dB, only minus 20 dB per decade. So, if you know K by S separately and all other factors separately, just we can add like this. So, this is, you should learn how to draw rough frequency response for given transfer function. But for examination, there is a procedure because they may expect if you draw directly, how the mark will be given. That's why we have to draw a table and how we are adding that and all we have to tell. That we will see now.